and this is existence. We don't know what exactly L is, but it's supposed to converge. Okay? And just the convergence, if that happens, we say it's convergence, approaching something. The convergence information itself is sometimes important. And you will see various tests will be, a convergence test will be prepared, but it all says about convergent, divergent, not necessarily letting you know that what this L is. Here's one example. This is done recursively, right? So at this point, we don't know what the closed formula of AN is, but it is possible that you can compute that. But at this stage, we'll treat it as something we don't know, all right? You can see that 1/7 going in, keep repeating, you know what those are. All right, what does it say at the bottom? We're going to introduce a technique, something called mathematical induction. We're going to establish boundedness. We're going to establish monotonic property. Okay? All right. Mathematical induction. What is mathematical induction? If you have some observation and you want to show that this observation is true from the data, like computer and data, right? Okay. So that's pretty much what it is. And here's some new technologies now kicking in. All right. Here's the 4 steps. You can write this one down, and I will give you an exercise to writing these 4 steps down on your own. So let's try to remember to get used to this very, very important idea. I will summarize it. And these are the important tools in the series and that. So this is one of them. All right. First, you compute several or many terms to formulate observation. In this case, 2 properties we'd like to formulate observation. One is boundedness. We want to show this is bounded, right? You look at the first few terms, that was actually our mathematical problem. When you sketched it, were you convinced that mathematical problem that was bounded? It actually grows like some big number if you look at more and more, right? So I wasn't convinced that it's actually bounded. It's probably unbounded. If you keep looking at bigger and bigger and more longer and longer term, maybe it keeps growing. But unless you mathematically prove it, you never know when it stops, right? So that's why we want to show it's bounded. And also, what is the second condition for bounded monotonic sequence theorem? Non-incremental. So those are the property. If you look at the computer data, it keeps going down. Hey, it's decreasing, but it might change later on. So we have to prove it using mathematical induction. It actually happened forever. You want to guarantee that. So first, you formulate observation, right? Second thing you have to do is that clearly state. Maybe how many things are 2 things, right? Bounded and monotonic. That's what you're trying to prove. Then it's 2 statements, right? So make sure you clearly state a statement with a parameter n in it. That's what this one is, right? And then try to prove it. So clearly state the statement you're trying to prove. These 2 steps are usually not part of inductions. They usually introduce the third, but I find it is an important part of induction, right? Third one, all right. Very first case are usually small numbers, right? Usually small numbers. So you can plug in and see if the statement you stated there for n equals 0, n equals 1 is satisfied or not. There's no mathematical reasoning in here. I calculated it, then calculation satisfied the property, right? It's kind of checking. The word verifying is used there, I think. Now, next thing is a little bit strange. We don't know what n is, but we assume for that specific n we might have, the statement is established, such as the very first one. I plug it in there and verify that P0 is true. The statement with parameter n equals 0 is true. So that's kind of the situation we're assuming here. Assume we have established certain fact that Pn for special value of n. Doesn't matter how you establish it, you have that when verified. Then can we use logic and this condition here we assume, combine and manipulate to get this Pn plus 1 is also true. But this n is not actual number. It's not actually 2015 or anything. It's just n. But it's a logical structure. Suppose we have that. To go from Pn to Pn plus 1, if that's very consistent, you'll be able to do that with this arbitrary letter n. Suppose you did that. I don't know what that n is. If I assume this is true, then I can show that Pn plus 1 is true. Then what that does is that I already verified that P0 is true. Therefore, according to that argument, P1 is true. I verified P1 is true. I mean, established that by logical connection. Then this argument again applies, telling you P2 is true. Now, once you have P2 is true, then P3 is true, and so on. So mathematicians believe that if you prove it in this fashion, we believe we establish that fact. Eternity. It happens forever. Okay? That is called what? Mathematical induction. So why don't you state those 4 steps that and get used to it. Or as you write those down, this kind of structure makes sense, and understand why mathematicians would believe that actually doesn't matter how n is big, that property will still be true. Kind of chain reaction. Don't you think this is what kind of entails? All right, so that's that. So let's see if we can actually establish these 2 facts there. Is this bounded or something? All right. How about boundedness? So let's write that down. This is an example that we're going to start together. Yes, did you have a question? No? I thought you had a question. All right, I'm going to skip some steps here. This formulating part. We want to show it's a bounded, right? It's bounded. And if it is increasing, what do you want to do about that? If it keeps increasing, we want to show it is bounded above, right? If it's decreasing, we want to show it's bounded below and things like that. So I will definitely compute several terms here. A2. How do you compute A2? You multiply 7 over 2 to the A1. So that's A1 here, correct? And plus 3 over 2. 3 over 7. So A1 is that, and multiply by 2 over 7. That makes this A1 smaller, don't you think? Multiplying 2 over 7 to give a number makes it smaller. But it compensates a little bit. It gives you a little bit more in there, and you're thinking about, is it bigger or something? So what is this number here? Is that 2 and plus 21? So is that 23, you think? Is that bigger than 1/7? Definitely bigger than 1/7, right? Yeah. If it's a 7, over there it's going down there. Did I have this right? 7/21. So the A1 is 1/7, and this one is greater than 1. So it seems like A1 is A2 is greater than A2. A2 is greater than A1. Excuse me. So we don't know if it's actually increasing or not, but suppose you calculated all that, it turns out first few terms is increasing, and you want to show why this one's increasing. Does that make sense? All right, what is Pn then? This is the tricky part. You want to show what is the statement that depends on your P, right? But what we want to show is increasing. So how do you formulate increasing property in mathematics? An plus 1 is bigger than An, right? This looks like a good statement. An plus 1 is bigger than An. All right? But it's equivalently also stated like this. It's a different version. An plus 1 minus An is greater than 0. That's always true. But if it is if you know it's a non-zero, and if it is a positive or something like that, and then you can also think about quotient, sometimes this is more convenient. If it is increasing, what do you think about the size of this number? This is greater than 1. But to enter that, you've got to have a property that An is always a positive, a non-zero, and things like that. Does that make sense? Because you're dividing the inequality. To go from here to there, you need that 2 property, An being positive, and so that requires more conditions there. But it seems like sometimes this is the nice thing to do. So let's focus on this one. When n is something, we want to show an plus 1 minus an is greater than 0. That's a statement. That's Pn. We want to establish that, right? Okay, so that's the part, first two part. This is observation part. You state it clearly. In a form, it is provable. Not saying increasing. That's not really a good statement that involves n in there. Okay, so what is the third step? If this starts from 1, what should be the statement you have to verify? Verify P of 1. That's the very, very first case, right? So let's go and state that. What is P1? N equals 1 is A2 minus A1 is greater than 0. This is what you have to verify, right? So what is A2? 23 divided by 7 squared minus A1, 17. Turns out it's actually greater than 0. So we verify the P1, right? Okay, let's go. How's the last step? This is the key step. Yeah. Usually in textbook they only write down this part and that part. They don't really make these two previous part as a part of procedure, but that's how it really happens. So we assume what? Pn is true for some specific. They usually say just some. And that includes 1, right? We showed that it's 1. For some n which is greater than or equal to 1. Versus for all n greater than or equal to 0. That's what we want to prove, right? We don't know if it is for all n, but for some n we establish that. And we want to prove Pn plus 1. Is that right? We want to go Pn plus 1. So what is Pn plus 1? Pn plus 1 is a statement that says an plus 2. Is that right? If you replace that n with n plus 1. Do you believe that? Minus an plus 1 is greater than 0. That's the statement we want to prove. Is that right? So let's consider, this is a statement to prove. Let's consider that this difference, an plus 1, an plus 2, minus an plus 1. So what are you going to do? What are you going to do about this statement in here, this equation? Right, solve for it, but what are you going to use to kind of rewrite that an plus 2? I think is, I don't know what's going on here. Only thing we know about this an is this recursive relation, right? So why don't we use that? What is the recursive relation applied to an plus 2? 2 over 7, an plus 1 plus 3 over 7. Don't you think? That's what an plus 2 is. If you go ahead and plug an plus 2, replace that with m plus 2, if you like, then that becomes m plus 1. So you fit in there. Does that make sense? How about an minus an plus 1? That's exactly what this one is. So here, 2 over 7, an plus 3 over 7. That's what this two quantity is about. Make sense? So what is it? 3 over 7 cancel, and 2 over 7 is common. An plus 1 minus, what is it? An, like that. So an plus 2 minus an plus 1 is 2/7 of an plus 1 minus an. Okay? So here's a time where we use this. This statement here is called induction hypothesis. Right? So this is a step where you use induction hypothesis. IH. Do you see? What is the statement Pn? An plus 1 minus an is greater than 0, right? So we know this guy is greater than 0 by what? By what reason we don't know this is greater than 0? Because the induction hypothesis, so by IH. Is that right? Therefore, positive times 2 over 7, which is still positive. Therefore, it's a positive. Correct? So I showed that a plus 2, Pn plus 1 is also true, using Pn and some algebra. Correct? All right. So let me go back to the outline. And here is the induction outline. We prove the very first case, P1. We assume Pn is true. Using recursive relation and logic, it's a little bit of algebra, we show Pn plus 1 is true, no matter what your n is. So therefore, you can keep going forever until you hit whatever arbitrarily large size of n is there. So, proof structure makes sense? So you write down and look at the mathematical data. See, they're all decreasing. I want to show it's always decreasing by using the induction and things like that. So what have we proved so far? The sequence is increasing. That's right. We prove the sequence is increasing. Then what do you want to show now? You started with 1/7, and you know it's always going up, right? 1/7. Next number is bigger. Next number is bigger. So do you want to show really it's bounded below? Kind of given free. That is always bounded by 1/7. Everything else is bigger, right? So it's bounded below by 1/7. But we're not sure it's keep increasing. Maybe go to infinity. Maybe it's bounded by something. All right? So that one, maybe you have to compute it further to get an idea what is the number it's bounded. Once you start with 1/7, so let's look at the structure in here, the boundedness. An plus 1 is a 2/7 an plus 3 over 7. I'm just guessing in here, not knowing the answer. But if you look at the data, which is usually the first step, you kind of have an idea that later on it's not changing, it's almost becoming like 6.3 or something. And then you try to show, oh, that's probably bounded above by 7 or something. So I'm going to replace this an by, if an is bounded by something, I don't know what it's bounded by. But if it is really an is bounded by something, I'm going to call that m. And then it's like this. Kind of give you an idea where it's going. Then I want to show the an plus 1 is also bounded by m, right? Isn't that the inductive structure? If an is bounded by m, then m is going to replace that and get it big, makes the whole quantity bigger. Does that make sense? So that's the induction hypothesis. But that only shows the an is smaller than m. We want to show is that this n plus 1 is also less than m. One way for that to happen is that this quantity is actually smaller than m. Right? If that happened to this value m and m, then we have a desired result. Okay, I don't know what that m is, but if m has a property like that, then induction hypothesis and this property allows us to conclude an plus 1 is also less than m. Therefore, inductively, this happens forever, whatever that m is. Does that make sense? This is not the proof. This is a process of discovering that upper bound without even looking at the computer data. But if you look at the computer data, you usually have a clear idea. And if you try that with the induction, it'll work, usually, because it's a fact. You can easily show that. But if you did not know and want to be clever, and this is one way, if an is bounded by m, I want an plus 1 also bounded by m, and if I pose this condition on m, then it happens. So what number that has this condition? M, here's a 3 over 7, less than, what is it? 5 over 7, I think, right? So if m is greater than 3 over 5, then it'll happen. This will always happen. So why don't I just choose 1? So what is clearly the statement Qn that we want to prove? Anybody? I discovered upper bound m being 1, so an is less than what number? 1. Could be 2, could be 3, always work. It's bounded, that's all we care. So, do you want to try that one? Proving an is always less than 1. That's your exercise. How about that? Fair enough? So, in this part, you don't have to go through this first statement, or 2. I stated for you, Qn, and we went through some, let's say pretend we went through some mathematical computation. We realized that that's all below 1. So why don't we prove that? Make sense? All right, was that okay? Now we know an is less than 1. Then an plus 1 is by recursive relation 2 over 7 an plus 3 over 7. Now this is less than 1, so if I replace an with the larger number, the whole quantity necessarily get bigger. So this quantity is 5 over 7. Still less than 1. So an plus 1 is also less than 1, if an is less than 1. So this argument repeatedly to all the indexes beginning with the very first case we established, and we believe that's always true. Logic makes sense? All right. So finally, we have proved this sequence. We don't even know how it looks like in the long term. This is always bounded above and below by what number? an is less than 1, but greater than equal to what number? 1/7. That's how we start. And we show is increasing, so it's always greater than 1/7, right? So it's in between 1/7 and 1. That's all these numbers. And we show that it's increasing, correct? Yeah. So then what do we know? That's the end of the induction on 2 statement, but we did that to establish boundedness and monotonic property, right? Then what is the bounded sequence theorem says? This guy's going to L, right? We don't know what L is, it's going to L. All right. So where is this going? Right? You can't always do that, but in this recursive relation, once you establish the convergence, you can use this recursive relation to compute sometimes what it is. It's a nice little trick. So I write it as an application of bounded monotonic sequence theorem, right? So where it's going. Here's the key. We know the limit of an plus 1, an exists, right? And they're always equal. So think about left-hand side, limit of the left-hand side. Hope this logic makes sense. Limit of the left-hand side. What is it? Limit n approaches infinity, an plus 1. We know it exists, right? This is where we use BM, the bounded monotonic sequence. We know this one exists, right? That existence. So we can call that L, correct? Whatever that is, it must be L. It exists. Doesn't matter if n plus 1 or n plus 2, n plus 2015, they're all going L, right? What is the limit of right-hand side? Limit n approaches infinity of 2 over 7 an plus 3 over 7, right? Then what kind of result do we use to kind of do something about this right-hand side? Let's go through some of the theorems. What are the result? Squeeze theorem? Not really. Geometric sequence theorem? Not really. Growth rate? Not really. How do you kind of change this expression in right-hand side or simplify? What do we use? Limit laws, right? Here's one sequence, constant sequence. It distributes, and there's a constant multiple you pull out. Remember that? So if I go from like this and distribute the limit like that, and limit 3 over 7, there's no n in it, so it's kind of trivial. So you can do like that by which result? LL, limit laws. Limit laws allows you to do that. But do you know there's a hypothesis in a limit law? Do you know what the hypothesis in a limit law is? It exists. If you read the first two sentences, it requires those sequences must exist. And this seems like a statement that nobody pay attention. Of course it exists, and then technical detail is what they pay attention. But the whole deal here is that we have to establish that they exist. Then we can do this business. All right? So what is this one then? L, right? Isn't that L? Same L? So right-hand side and left-hand side, both sequences exist, and its limit must exist. I mean, limit exists, therefore they should be equal to each other, right? The same sequence here, same number. So we enter, finally, that by hitting the limit in here and there, we enter logically the limit of left-hand side, which is L. Limit of right-hand side is a 2 over 7, L plus 3 over 7, right? We know L must exist. Then it says L is must satisfy this number. Any real number that satisfies this condition is called 5 over 7, L equals 3 over 7. And what is L? Three-fifths. Must have approached 3/5. Isn't that cool? Yeah. Bounded monotonic sequence theorem allows you to conclude it exists. Once you exist, the limit law allows you to conclude what that convergence point must be. All right? Any question about this line of thinking? There you go.